So the point of our first example is to show you how being greedy in different ways can affect the final result. So it's the activity selection problem. So we have a set of activities that wish to use a resource, for example, a classroom. And each activity takes place during a time interval, starting from S, that stands for start, and F stands for finish. So from the starting time to finish time, and this is a half open interval. We say two activities, A sub I and A sub j, are compatible if the I's activity starts after the J's activity finishes, or the other way around, which means that their time intervals do not overlap. That's what being compatible means. And our target is to select a maximum size subset of mutually compatible activities. And we assume that they are sorted according to their finish times. So basically, we have like one classroom and we have N student clubs who would make reservations. Now let's sort them according to their finish times. So the question is, how can we make everyone happy? And if that's impossible, we will try to make as many people happy as possible. For example, say here we have 11 activities, say 11 student clubs, and these are their start times and these are their finish times. To help you understand this, let's draw the figure here. So this is the total time interval from 0 to 16, the largest finish time. 0 is the smallest starting time. Okay, and these are the intervals. A mutually compatible set is something like this. So for example, if we schedule these three activities, their intervals do not overlap, so they are mutually compatible. So take a moment and think about what the maximum size is. 4, right? So for example, this is one optimal solution. We can actually schedule 4 clubs. But on the other hand, the optimal solution is not unique. For example, this is another one, right? We can also schedule these 4 clubs. So now here comes your first discussion question here. How can we be greedy? Well, there's certainly more than one way of being greedy here. But before we jump into it, let's think about dynamic programming for a while. If we think about DP, it's actually quite straightforward, right? First, let's define the subproblem to be the activities from A sub I to A sub j. And let's make it an open interval, which means this S sub ij contains of activities that start after A sub I finishes and that finishes before A sub j starts. So it's an open interval, and A sub I and A sub j are not included in this S sub ij. And then let's think in a divide and conquer way. Let's partition S sub ij into 2 parts. If this set is not empty, well, obviously we can collect at least one activity, right? So for any A sub k, if we collect this A sub k into our solution, then the optimal solution for S sub ij must be 1 for that A sub k, plus the optimal cost from A sub I to A sub k and the optimal cost from A sub k to A sub j, where both are open intervals. And of course, they must be mutually compatible. And that is for one A sub k. And since this is the optimal solution, we take the maximum for all those A sub k's. check each one of them, and finally take the largest number. And of course, if this is empty, the optimal solution is 0. So what is the time complexity? This is for C sub I and j, and the range for both I and j is from 1 to n, right? And obviously, the time complexity would be big O of n squared. But the question here is that, is it really necessary to check all the possible cases? Can we simply choose the right one and collect it? So is there any way to know who's the best choice? So the question here is, can we be greedy here? And the answer is, yes, we can. Just be greedy. Then the next question is, how? There are many different ways of being greedy. Let's check them out one by one. So greedy rule number 1. Let's select the interval which starts earliest. But certainly they have to be mutually compatible. Okay, how about that? Is it correct? If you don't think so, can you give a counterexample? Here we go. See, if this is the situation and we select the interval which starts earliest, we're supposed to take this one because that one starts the earliest. And if we take this one, there's no way to get the correct answer. So it doesn't work. It seems like the problem is we have chosen a very long interval. And if we decide to choose a shorter interval, we might be able to get a better answer, right? And therefore, here is the rule number 2. Let's select the interval which is the shortest. Will it work? Can you think of any counterexample? Okay, check this out. Well, this one is the shortest. However, it conflicts with both intervals. And therefore, if we choose this one, again, it doesn't work. According to this counterexample, it seems like if an interval has many conflicts with other intervals, we should not choose that one. And therefore, we have our greedy rule number 3. Let's select the interval with the fewest conflicts with other remaining intervals. How about that? Can you think of any counterexample? Well, look at this one. So the red intervals are correct answers. However, each of them will have many conflicts. Well, this interval looks the best with this criterion, right? But if we select this one, we won't be able to choose these two. And therefore, the solution we obtain will only contain at most 3 intervals instead of 4. So that one doesn't work. Now, let's check out greedy rule number 4. How about selecting the interval which ends first? Which means we would like to make the resource become free as soon as possible. Okay, and with this rule, let's check out the previous counterexamples. So in this case, this activity is the one that ends first. So we're supposed to choose this one. If this one is selected, then this one is out, and therefore the second one will be available, and we can obtain the good result. And how about this one? In this case, this one ends first. And if this one is taken, none of those black activities will be chosen, and therefore the next one will be collected, and so on and so forth. So that one works. So how about the first one? The first example is like this, right? And this activity is the one that ends first. So we're gonna select this one. Once this one is collected, the black one will be out, and therefore we can obtain the correct answer. So far it looks like greedy rule number 4 works pretty well. So you see that To pop a greedy method from the top of your head is easy, but we ought to be careful about its correctness. That's the hardest part, right? So we must prove at least two things. One, the solution we obtained from greedy method is feasible and it satisfies all the constraints. So in this example, all the activities we collect must be mutually compatible. And the second is, of course, the result is indeed the best. So here is one theorem saying that consider any non-empty subproblem S sub k and let A sub m be an activity in S sub k with the earliest finish time. Then this activity is included in some maximum size subset of mutually compatible activities of S sub k. So what it's saying is that for any subproblem S sub k, there may be many optimal solutions, and the solution may not be unique, but there must be one optimal solution that contains the activity with the earliest finish time. So if we can prove this conclusion, then we can select one that finishes the first and then recursively solve the rest, which is another subproblem. And so this conclusion is also true for that subproblem. So we can just keep going like this. And that proves the correctness of this greedy algorithm. And the proof is simple. Just let A sub k be the optimal solution set, which does not necessarily contain A sub m. But it must have one activity that finishes first, right? And so let's call it A sub EF, that's earliest finish, A sub EF. Okay, then we have two possible situations. Okay, if A sub m and A sub EF are the same activity, then we are done. Otherwise, if they are not the same, let's try to replace this one by A sub m and get another solution. So will it change anything? So the key question is, can we actually do so? Will this A sub m be mutually compatible to the rest of the activities in A sub k? Well, since A sub m is the activity in this set with the earliest finish time, so its finish time must be smaller than or equal to the finish time of A sub EF, right? Because that is the one that finishes the first. Okay? And if this one is mutually compatible to the rest of the set, certainly this one will have no conflicts. And therefore A sub k prime, this set is another optimal solution, because the number of activities that can be scheduled remains the same. We simply replace one activity by another one. And that finishes the proof. So according to this theorem, the implementation of this algorithm could be, we select the first activity according to their finish time, take the earliest finished activity, and then recursively solve for the rest. And since this must be a tail recursion, we can remove the tail recursion by iterations. So the total time complexity would be the time taken to sort their finish times, and that's n log n. And the rest can be done in linear time. Finally, we can claim that being greedy according to rule number 4 actually works. Okay. Here's one more question. How about collecting the activity that starts the latest instead of finishes the first? Think about it. And the answer is yes. So see that there's more than one way to solve it, and you can try to prove it if you're interested. Now, let's take another look at the DP solution. It seems that we do have an optimal substructure, do we? The optimal solution contains optimal solutions to subproblems, And since the greedy method works, it can be reduced from two-dimensional to one-dimensional. So we can fix one end and therefore only consider the subproblems starting from 1 instead of considering all pairs of I and j. So for each a sub j, we have two options. Either we take it, so 1 is for taking that a sub j, and then the rest of the problem becomes another subproblem starting from 1 and to some a sub k of j, which is the nearest compatible activity to a sub j that is finished before a sub j, right? So this will be the optimal solution of that subproblem plus taking a sub j into account. Or if a sub j is not taken, it will be the same as the optimal solution from 1 to j minus 1. So it seems like both algorithms work. Well, we have some kind of optimal substructure. Well, if each activity has a weight, if our goal is to maximum the total weight instead of the number of activities, can we simply replace 1 by the weight? How about this? And there are two questions. One, is the DP solution still correct? And the answer is yes. And the second one is the greedy solution still correct? Not really. Why not? Well, I would suggest you to think about it by yourselves after the class. All right? So the point is, when we can actually apply greedy method to obtain the optimal solution. So here we have the elements of the greedy strategy. Basically, there are three key elements. The first one is we may cast the optimization problem as one in which we can make a choice and are left with one subproblem to solve. So basically, we're solving the problem step by step, and at each step, we make a choice. And secondly, we must prove that there is always one optimal solution to the original problem that makes the greedy choice, so that the greedy choice is always safe. So it's just like what we have proved in the previous theorem, saying that although there might be many different optimal solutions, there must be at least one solution that contains the greedy choice. And finally, we must demonstrate that this problem has optimal substructure by showing that having made the greedy choice, what remains is a subproblem with the property that if we combine an optimal solution to the subproblem with the greedy choice we have made, we arrive at one optimal solution to the original problem. So basically, greedy works only if we have this kind of simpler optimal structure, when the optimal solution is just one greedy choice plus the optimal of subproblems. And the relationship between greedy method and the DP is that beneath every greedy algorithm, there's almost always a more cumbersome dynamic programming solution.